Welcome back. I'm Mike Yawn, a Senior Solutions Architect with Hazelcast, and you're watching Television. Today's topic is entry processors. Even in the earliest versions of Hazelcast, before there were cool features like stream processing, SQL support, and support for AI and ML workloads, there was support for distributed compute capabilities. These capabilities are the bedrock, if you will, of what makes Hazelcast more than just a simple cache. Entry processors are a great starting point for beginning to explore the distributed compute capabilities of Hazelcast. An entry processor is a piece of code that's part of your application, but which is submitted to the cluster for execution, where it will run against the data stored in an IMAP. Entry processors can help your code run faster. You'll spend more time doing useful work and less time shoving data back and forth across the network. You'll get more concurrency because operations on different partitions can be processed in parallel. And for multi-step operations, like a fetch, update, and put sequence, the entry processor will execute atomically, so you don't have to lock around the operation, which would further slow things down. Here's the complete entry processor API. In most cases, the only method your entry processor needs to implement is the process method. It takes a single argument, which is the map entry the processor will operate on, and it can optionally return a value, which could be the map entry, a value from the map, or anything else you choose. Now, by default, the processor will run against both the primary and the backup entries in the cluster. If you want backups to be treated differently, you can implement the optional getBackUpProcessor API. An entry processor is invoked by calling one of these methods from the IMAP API. They will apply the entry processor as follows. So the first method executes the processor on all entries in the map. The second method will apply the processor to all map entries that match the predicate. So essentially, filter the map and then apply to all the entries that pass the filter. The third variation is to apply the processor to a single entry identified by the key that's passed in. The fourth entry is similar. It applies the processor to all of the entries specified by the set of keys that is passed in. And then finally, we have asynchronous versions of the last two. So you can submit the entry processor for execution, and you'll get back a completion stage that you can use to monitor the status of that processor's execution. So let's see what an entry processor looks like and what a difference it makes. We're going to use a trivial use case. We'll create a map that just holds counter values and then update all of the counters. We'll do this first without an entry processor and then with one. We'll do 10 increments for each of 1,000 keys, so our total will be 10,000 operations. Here's a first pass at writing what I call the naive client, the one that doesn't use an entry processor. We have an outer loop that runs times to increment times, which is 10, and an inner loop that runs for the count of entries to process, which is 1,000. In the body of the inner loop, we simply get an entry from the map, increment it, and then write it back. If this was run against a local map, it would be very fast. I actually tried this, and it was a little over 300 milliseconds for the 10,000 operations. But for a remote map, this is a terrible design. We're doing a round trip across the network for every get, and then another round trip across the network for every put. So I tested this naive client running from my laptop in Atlanta and connecting to a Hazelcast cluster deployed in the AWS US West region, US West 2 region, which is in Oregon. I ran the client 3 times, and on average, the elapsed time was over 26 minutes. That sounds horrible, and it is. When you start quoting response time in minutes, you're not in a happy place. So if we break that down for our 10,000 operations, it's roughly 156 milliseconds for each entry, which is actually not bad given the physics. My ping times to the region were in the range of 82 to 84 milliseconds, so getting 2 round trips in 152 milliseconds is actually better than we'd expect to achieve. So the takeaway here is that pretty much 100% of our time is network latency. Not surprising because incrementing a counter is about as trivial as it gets. But this is also doing SSL encryption of the payload, and we are serializing and deserializing values at each end. So it wouldn't have been surprising if we'd seen some additional delay show up in the timing. But it's about to get worse because this code isn't correct. My first test was single-threaded, so the results came out all right. But if I have multiple threads doing the counter updates, I'll lose updates because there's no locking here. To make this thread safe, I need to lock before the get and then release the lock after the put. So here's the same code with locking added. The unlock should really be in a finally block, but it won't affect the timing. So this shows our correct implementation of the naive client. So we now have 4 round trips for each increment of our entry. The time per entry is roughly 3¼ seconds. So for the entire workload, we're looking at about 54 minutes. This is truly a Stone Age approach to distributed compute. Yabba dabba don't. So how do we do this with an entry processor? Here's the code. So we start out by defining our entry processor. We could define a class here if we wanted, but since things are simple enough, we'll just use a Lambda function to implement the entry processor's process method. We do a get value to retrieve the current value of the entry, we increment it, and then we do a set value to write it back into the map. Very simple. Then we use the execute on entries method of the IMAP to execute this entry processor against all entries in the map. Recall that IMAP gives us several different APIs depending on whether we're targeting a single entry, a set of entries, or all entries. We also wrap this in a loop because we wanted to increment each entry 10 times. Now we could have made this part of the entry processor itself very easily, but I didn't choose to go that way. So when we run this version of our code, our overall time dropped from 54 minutes in the naive version to under a second, 877 milliseconds specifically, and this was doing 10 round trips to the remote data center. And as we just said, we could actually cut that by 90% and have just a single round trip if our entry processor was told up front how many times to increment each entry. So we can conclusively say that when using a distributed cache or distributed data store, if you're not taking advantage of distributed compute, it's just not a great design choice. So let's wrap up today with some cluster facts about entry processors. Entry processors accelerate applications by reducing the round trips across the network, and also by reducing or eliminating the need to hold locks during updates. The body of an entry processor should only modify a single entry. By using IMAP methods that target groups of entries, a single invocation may update many entries, but the entry processor implementation itself should concern itself with just a single entry. Entry processors run on the cluster nodes, and specifically on the partition threads, so they provide concurrency with no coordination effort on the developer's part. If you're doing something substantial in an entry processor, you can make it offloadable so it doesn't block the partition thread. So that's our look at entry processors. Tune in to our next TellUvision where we'll take a look at more interesting Hazelcast technology.